Hello everyone. Do you hear me? I just want to confirm that from the chat if there is some image, if there is some stream from me, there is some sound. So I suppose to start it. Okay, perfect. My God. Well, it was some issues. I mean, technical issues. I was so excited that I forgot which button I have to press. So don't worry, I'm ready, and I guess you're ready too. So, uh, from very beginning. So today's lecture is about the pathomorphology of infectious diseases. To prove the relevance of the study of infectious diseases is definitely time wasting at the present. However, traditionally, the first minutes of each lecture are dedicated to this. And not to forget that humanity is not only suffering from COVID at the moment. Take a look at the following slides. If we compare the mortality structure of the regions with the most developed economies in the world, the American, European, Western Pacific, we can see that the leader places in the race of the killer diseases is holding by cardiovascular and cerebrovascular diseases. The so-called communicative diseases are represented only by lower respiratory tract infections on 6th, 7th places. The situation is slightly different in the Southeast Asian and East Mediterranean regions. Lower respiratory tract infections have climbed to 3rd, 4th place. Diarrheal infections in red and tuberculosis have here. Well, the most extreme situation in Mother Africa. Coronary heart disease retreated to 4th place before pneumonia. HIV infection and diarrhea infections, malaria and tuberculosis take 5th, 6th places. Socioeconomic factors are obviously the reason of such epidemiologic conditions of human cradle. On the common map, mortality rate due to infectious diseases is shown varying from minimum intensity, you see that in yellow, to maximum in red. So the top 3 primary diseases are HIV, tuberculosis, and malaria. While the number of deaths from almost every disease has decreased over the past 10 years, deaths from HIV have quadrupled. The most important childhood diseases include whooping cough, polio, diphtheria, measles, and tetanus. Children also account for a high mortality rate from respiratory infections. In 2012, approximately 3 million people died from lower respiratory tract infections, making this group of diseases fourth the leading cause of death in the world. So, when you listen to a lecture on infectious diseases, it's important to understand that that's the group of diseases is the result of interspecial competitive interactions with pathogens. So on one side, that's us, humans, and our counterparts, that's the microbes. This result in a set of pathological, adaptive, and reparative reactions of the body to infection. So, as you may see, the term infection is not identical to the term infectious disease. In general biological terms, the relationship between two distinct but associated organisms can be classified as parasitic, where one benefits at the expense of the other, or symbiotic, no, in other words, mutualistic, where both benefit. There is another commonly used category called commensalism, whereby the organism coexists without damage to either organism. The classification system can be applied to the association between microorganisms and vertebrates. Generalized infections such as HIV, tuberculosis, or typhoid are clearly examples of parasitism. On the other hand, the microbiota inhabiting the small intestine enjoying food and shelter and at the same time benefit the host by collecting the energy from the fermentation of undigested carbohydrates, synthesizing vitamin B and vitamin K, as well as metabolizing xenobiotics. So they are clearly mutualistic. In addition, recent and ongoing research is revealing that the great variety of ways in which resident bacteria are contributing to the normal function of the host species. For example, axis, microbiome, gut, brain. Only a tiny proportion of the microorganisms associated with humans have the potential to give rise to pathological changes of cause of disease. So just try to memorize that. Only tiny proportion as our enemies. Vast numbers of bacteria live harmlessly in the mouth and in intestines, on the teeth and skin, and most of the 150 or so viruses that infect humans cause no detectable illness in most infected individuals. So you see, for that appears the term virome. In the body of a healthy person can live approximately 100 types of viruses, and some of them, like bacteriophages, have a protective role. So this is to be expected because from an evolutionary point of view, successful microbes must survive, multiply, and leave viable descendants. A successful parasitic microbe lives in or in the individual host, multiplies, spreads to fresh individuals, and thus maintains itself in nature. A microbe's ability to multiply is obviously of paramount importance. Indeed, we call a microbe dead or non-viable if it cannot replicate. The ability to spread from host to host is of equal importance. Spread can be horizontal in a species, whereby one individual infects another by contact or via insect vectors. Also, you may see the zoonosis. Alternatively, spread can be vertical in a species with parents infecting offspring via sperm, ovum, the placenta, the milk, or by contact. Clearly, if a microbe does not spread from one individual to another, it will die with the individual and cannot persist in nature. The crucial significance of the ability of a microbe to spread can be illustrated by comparing the horizontal spread of respiratory and sexually transmitted infections, STIs. An infected individual can transmit influenza or COVID-19 to a score of others in the course of innocent hour in a crowded room, but any STI also must spread progressively from one person to person if it's maintained itself in nature. But even the most energetic lover can transmit a venereal infection on such a scale. A successful parasitic microbe, like all successful parasites, will obtain what it requires for proliferation from the infected host without causing much damage. If an infection is debilitating or even lethal, there will be a reduction in numbers of the host species and thus in the numbers of the microorganism. Thus, although a small number of microbial pathogens cause disease, and majority of those infected, so-called true pathogens, most are comparatively harmless, causing either no disease or disease in only a small proportion of those infected. Polioviruses, uh, John Cunningham virus, for instance, are transmitted by fecal-oral route and causes subclinical intestinal infection under normal circumstances. But in an occasional host, the virus invades the central nervous system and causes meningitis, sometimes paralysis, and very occasionally death. Thus, particular site of multiplication is irrelevant from the virus point of view because growth in the central nervous system is quite unnecessary for transmission to the next host. Well-established infectious agents have therefore generally reached a state of balanced pathogenicity in the host and cause the smallest amount of damage compatible with the need to enter, multiply, and be discharged from the body. Although successful parasites cannot afford to become too pathogenic, some degree of tissue damage may be necessary for the effective shedding of microorganisms to the exterior. As for instance, in the flow of infected fluids from the nose in the common cold, or from alimentary canal in infectious diarrhea. Otherwise, there is ideally very little tissue damage, a minimal inflammatory or immune response, and few microbial parasites achieve the supreme success of causing zero damage and failing to be recognized as parasites by the host. Different microbes show varying degrees of attainment of this ideal state of parasitism. And the concept of balanced pathogenicity is helpful in understanding infectious diseases. But many infections have not yet had time to reach this ideal state. You see them here. In fact, they have been responsible for the great pestilences in history, have at times determined the course of history, like now, and continue in spite of vaccines and antibiotics as major cause of disease. How it's possible? What are the reasons of that? So in fact, each microorganism evolves, occasional virulent variants emerge and cause extensive disease and death before disappearing after all susceptible individuals have been infected or before settling down to a more balanced pathogenicity. So that's due to occasional mutation that suddenly increases the microbe's virulence. Secondly, microbe recently introduced into a host, like today's problem, SARS-CoV-2, may not have had time to settle down into this ideal state of parasitism. Thirdly, some of the microbes responsible for serious human diseases had appeared originally one part of the world, then had been introduced to another and caused such pestilences like smallpox in Japan or in America, so tuberculosis in Africa, again in the Americas. Well, finally, there are a number of microorganisms that have not evolved towards a less pathogenic form in man because the human host is clearly irrelevant for the survival of the microorganism. That belongs, for example, to plague and scrub typhus, leptospirosis, etc. So, as humans colonize every corner of the earth, they encounter an occasional microbe from an exotic animal that causes quite accidentally, like now again, so that's the red line of our lecture, from the point of view of the microorganism, a serious or lethal human disease. Examples include our current situation, so for example, Ebola too. So that's the very important slide about the virulence and pathogenicity of the microorganism and their ability to kill and damage the host that makes them important to the physician. Microorganisms multiply exceedingly rapidly in comparison to the vertebrate hosts. The generation time of an average bacterium is an hour or less, as compared with about 20 years for us. Consequently, microorganisms evolve with extraordinary speed in comparison with the vertebrate hosts. So you see that the race is quite unfair and not equal. Vertebrates throughout the hundreds of millions of years of evolution have been continuously exposed to microbial infections. They have developed highly recognition, early warning systems for foreign invaders, and effective inflammatory and immune responses to restrain their growth and spread and to eliminate them from the body. Unfortunately, these responses are not completely effective because microorganisms faced with the antimicrobial defenses of the host species have evolved and developed a variety of characteristics that enable them to bypass or overcome these defenses. If there are possible ways around the established defenses, microorganisms are likely to have discovered and taken advantage of them. Successful microorganisms indeed owe their success to this ability to adapt and evolve, exploiting weak points in the host defenses. So anyway, the interaction between the same host and the same species of the microbe can have quite different spectrum of manifestations. Such variation within the population is reflected in the concept of epidemiological iceberg, or rather pyramid. There is at the very top, there is the lowest percentage of infected with the most severe and obvious cases of infectious disease. For example, the same thing could be applied for COVID-19. And vice versa, in the basement of this pyramid, the highest percentage of infectious that have a mild form of infection, infectious disease, or even no or subclinical infection, which in the end will not be included into the statistics. Okay, if we're talking about infectious disease, we must discuss about how the infectious agents can entry and exit. Yeah, they apparently, in most of the cases, temporary guests. So microbes can enter the host by breaching epithelial surfaces, inhalation, ingestion, or sexual transmission. In general, respiratory, gastrointestinal, and genitourinary tract infections in otherwise healthy persons are caused by virulent microorganisms with the ability to damage or penetrate the epidermis or mucosal epithelium. By contrast, skin infections in healthy persons are mainly caused by less virulent organisms that enter the skin through superficial injuries, like biting, arthropods, or skin wounds. The intact keratinized epidermis protects against infection by serving as the strong mechanical barrier and by producing antimicrobial fatty acids and defensins, small peptides that are toxic to bacteria. We will discuss about them later. These and other substances secreted by the skin create an environmental niche that is occupied by potential opportunistic organisms. Uh, in general, microorganisms cannot traverse the unbroken skin. Exceptions include the larvae of schistosoma, which release enzymes that dissolve the adhesive proteins that hold keratinocytes together. Uh, gastrointestinal tract. So you see, most gastrointestinal pathogens are transmitted by food or drink contaminated with fecal material. Gastrointestinal tract infections may occur when local defenses are circumvented by pathogen or when they are so weakened that even normal flora produce disease. So many notorious gastrointestinal pathogens are intrinsically resistant to local defenses, particularly those that enter the host by ingestion, like Vibrio cholera, etc. And as you may see here, the enteropathogenic bacteria may establish symptomatic gastrointestinal disease through several distinct mechanisms. First, adhesion and local proliferation. Examples include Vibrio cholera and enterotoxigenic Escherichia coli, which bind to the intestinal epithelium and multiply in the overlying mucous layer. Here, these organisms elaborate potent exotoxins that are responsible for symptomatic disease. Uh, this list includes Helicobacter pylori, whose involvement in the development of chronic gastritis was proven relatively recently due to, must say, the scientific victory of a doctor from University Clinic in Western Australia. That's Dr. Barry Marshall and his colleague. He spent several months experimenting with animals, then gave up to have any success in this experiment and finally infected himself and proved that Escherichia coli exactly caused the gastritis and peptic ulcer disease. Finally, he and Robin Warren, they were awarded 20 years later with the Nobel Prize in Physiology and Medicine for the discovery of the bacterium Helicobacter pylori and its role in gastritis and peptic ulcer disease. So the second mechanism, that's adhesion and local proliferation. Examples include, adhesion and mucosal invasion. That's examples include Shigella, Salmonella, and exactly Salmonella enterica for typhoid, Campylobacter uni, and Entamoeba histolytica. These bacteria could invade mucosa and lamina propria and cause ulceration, inflammation, and hemorrhage that manifest clinically as dysentery. So here you may see the very tricky machinery which is applied by Escherichia coli, exactly enteropathogenic Escherichia coli, to invade the superficial layer of the mucosa. It used so-called translocon, the complex of proteins that helps these bacteria to invade the enterocyte. Next mechanism, that's literally hijacking of host pathways of antigen uptake. You may recall your histology course that mucosal lymphoid tissues melt, such as pair patches, are covered by specialized, very specialized epithelial cells called M cells, which are responsible for uptake and delivery of antigens to underlying lymphoid tissues. Ironically, multiple infectious agents, including poliovirus, are taken up into the host through this same pathway. Here you may see the Salmonella typhimurium, which is trying to invade the enterocytes. And here you see the result. So, development of the clinically manifested typhoid fever with so-called clean ulcer stage. So just notice the ulceration, necrotizing of epithelium, so it continues somewhere over there. Then, since that's already the chronic process, we see the development of the vessels here, that's granulation tissue, and participants of the chronic inflammation, mononuclear cells, mostly that's the highly vacuolated macrophages, and they are adjacent to the lymphoid tissue of Bayer patch. The next important route of the infections, that's the respiratory tract. Multiple microorganisms, viruses, bacteria, even fungi, we inhale them daily, mainly in dust or aerosol particles. The distance these particles travel into the respiratory system is inversely proportional to this size. Large particles are trapped in the mucociliary blanket that lines the nose and upper respiratory tract. Microorganisms trapped in the mucous layer are transported by ciliary movement to the back of the throat. There we can swallow them. That's the defense, very simple. So the microorganisms that infect the healthy respiratory tract evade local defenses through several different mechanisms. Some pathogenic respiratory viruses attach to and enter epithelial cells in the lower respiratory tract and pharynx, like influenza virus, have enveloped proteins called hemagglutinins that bind to sialic acid. They are very non-specific, and that's why no any antibody can block them. So they could be attached to respiratory epithelium and finally cause such kind of influenza pneumonia with the necrotizing of alveolar epithelium. You see the development of the diffuse alveolar damage with the development of the interstitial inflammation, and you see the hemorrhages. Actually, hemorrhages you may see on the lower power of this image. The same story for the SARS-CoV-2. This virus can attach to the specific proteins on the surface, including the respiratory epithelium, and finally attachment induces the host cell to endocytose the virus, leading to viral entry and replication. Certain bacterial respiratory pathogens, including Bordetella pertussis, release toxins that enhance the ability to establish an infection by impairing ciliary movement. You see the immunohistochemical staining confirm the presence of exactly this bacteria. And here you may see the result of COVID-19 development of the acute respiratory distress syndrome. On this image, you may see the formation of fibrous tissue that's already happened diffuse alveolar damage, but now that's in the healing stage. However, you may notice plenty of hemorrhages. You may notice the abscess of alveolar epithelium and very, very intensive interstitial inflammation. Mostly this inflammatory infiltrate represented by lymphocytes. Well, another important mechanism of establishing respiratory infection is primary resistance to killing following phagocytosis. Classic example is Mycobacterium tuberculosis, which gains a foothold in alveoli by surviving within the phagolysosomes and macrophages. Other organisms establish disease then when local or systemic defenses are impaired. For example, chronic impairment of mucociliary defense mechanism occur in smokers, and in people with cystic fibrosis. Many other infectious agents cause respiratory infections primarily in the setting of systemic immunodeficiency. Examples include fungal infections by Aspergillus, like here. You see the development of Aspergillus abscess on the lower power. You may see two focuses of this infection, and here you see the growing of the gypha of this fungi. The response is quite weak. see the not so much the neutrophils, and again quite rare occurrence of the macrophages. So look, well, some disease-causing microorganisms remain localized to the initial site of infection. Others have the capacity to invade tissues and spread to distant sites uh, by lymphatics, blood, or nerves. Pathogens can spread within the body in several ways. Some extracellular pathogens secrete enzymes that break down tissues, allowing the organism to advance virtually unimpeded. For example, Staphylococcus aureus secretes hyaluronidase, which degrades the extracellular matrix between host cells, allowing the microbes to follow tissue planes of least resistance. So eventually, the organism may travel through the lymphatics to regional lymph nodes and the blood, potentially leading to bacteremia and spread to distant organs, such as heart and bone. Certain viruses, such as rabies, poliovirus, and varicella zoster virus, spread to the central nervous system by infecting peripheral nerves and then traveling intracellularly along the dendrites and axons. However, the most common and efficient mode of microbial dissemination is through the bloodstream. Some blood-borne pathogens, such as certain viruses, poliovirus, hepatitis B, etc., most bacteria and fungi, some protozoa like African trypanosomes and helminths are transported free in plasma, while others are carried within leukocytes like herpesviruses, HIV, or red blood cells like Plasmodium myeloid. The consequences of blood-borne spread of pathogens vary widely depending on the virulence of the organism, the magnitude of the infection, the pattern of seeding, and host factors such as immune status. Sporadic bloodstream invasion by low virulence or non-virulent microbes during brushing of teeth, for example, is common but is quickly controlled by normal host defenses. So, there is little doubt that the ability to survive in a world full of pathogenic microbes was and remains one of the most important forces shaping human evolution. Unfortunately, Darwinian forces also drive the continuing evolution of the remarkable array of highly diverse microbes, which are constantly threatening to get a step ahead of host defenses. We will return to the issue of newly emerging infection a bit later. Then I will discuss about Ebola and COVID. Here we discussing about various mechanisms by which pathogens evade the host and cause disease. First mechanism, that's the modulation of surface structure, leading to antigenic variation, both bacteria or viruses. Most pathogenic microbes have developed one or more strategies that allow them to evade host defenses. So here you may see the major tools for antigenic variation include high mutation rate. You may apply that for HIV and influenza virus. The genetic reassortment, genetic rearrangement, and large diversity of serotypes. Second mechanism, that resistance to antimicrobial peptides. I already mentioned about defenses, they're quite important, and this second evasion mechanism applied exactly to protect microorganisms from this So resistance to these peptides is a factor of the virulence of a number of pathogens, including Shigella, Staphylococcus aureus, and Candida. The tool number 3, resistance to killing by phagocytes. Phagocytosis and killing of bacteria by neutrophils and macrophages are critical host defense against extracellular bacteria. So the carbohydrate capsule, as you remember, on the surface of many bacteria, like Streptococcus pneumonia, Neisseria meningitidis, Haemophilus influenza, prevents phagocytosis of the organism by neutrophils. E. coli that cause meningitis in newborns synthesize a special capsule containing sialic acid that will not bind C3b. Next tool, evasion of apoptosis. Have you heard about evasion of apoptosis before? Remember that was about the tumors. So now you may see that the intracellular parasites like viruses may manipulate the intracellular mechanisms against them, evading the apoptosis of the cell which is infected. The mechanism number 5, that's the resistance to cytokine, chemokine, and complement-mediated host defense. Example, some viruses like COVID-19 can defend themselves blocking the key signaling cascade that lies downstream of interferon receptors. So they just literally can block interferon production and thus can avoid this defensive mechanism. Next, evasion of recognition by CD4 helpers and CD8 killers. That's important mode of immune evasion by viruses, like several DNA viruses, cytomegalovirus, for example, Epstein-Barr virus, and herpes simplex virus, bind to localization of major histocompatibility complex. And in such a way, they impair peptide presentation to CD8 cells. Oh, tricky, very tricky. Another strategy, that's their downregulation of antimicrobial T cell responses. That's so-called mechanism of T cell exhaustion. So how they could be exhausted. For example, during chronic viral infections, antigen-specific T cells initially acquire effector functions, but then gradually they lose their potency as infection progresses. That belongs to HIV, hepatitis C, and hepatitis B viral infections. And the last strategy, that's the latency of the infection. Basically, that belongs to different viruses like herpes viruses, varicella zoster, Epstein-Barr. Also, we may find this mechanism in HIV infection development. So, what about the host? Now, the microbe is already invaded. It's already in our house, in our apartments. What they could cause? They could cause host damage. Infectious agents establish infection and damage tissues by 3 major mechanisms. First, they can contact or enter host cells and cause the death of the cells directly, or cause changes in cellular metabolism and proliferation that can eventually lead to transformation of cells. They may release toxins that kill cells at a distance, release enzymes that degrade tissue components or damage blood vessels and cause ischemic necrosis. After all, they can induce host immune response. Yesterday we discussed about sepsis, as you remember, and that's the good example how the bacteria or viruses may cause severe inflammatory response. So I would like to start exactly from the injurious effects of host immunity. So here you may see 6 major types of that. Host immune response to microbes can sometimes be a major cause of tissue injury, as you may see. Like then we have deal with the inflammatory reaction to Mycobacterium tuberculosis. At a glance, mycobacteria is becoming sequestered, detained, like behind the wall of the epithelioid cells. Epithelioid cells. That's very important. Epithelioid cells. So in such a way, it prevents the spread. But in the same way, we see the destruction and caseating, development of caseous necrosis of the tissue. So, damage to hepatocytes in case of hepatitis B. Do you remember? So, the damage to hepatitis B and their necrosis is occurring due to the activity of key killers. So, that's not the fault, or not direct fault of the HBV. That's the result of key killers. So, in one hand, that's good, but then the inflammatory response surpass the adaptation or compensatory capability of the host is becoming injurious. So let's talk about the heart of this lecture. Basically, it's focused on the viral infections, and now I would like to start the discussion about the mechanism of viral injury. First of all, let me recall you the classification of viruses. It's basically based on the DNA or RNA compounds in them. So you see the 2 major groups, DNA and RNA viruses. That's very multiple groups, and DNA viruses also could be divided into different subtypes, like double-stranded DNA viruses, single-stranded DNA viruses, and double-stranded DNA with reverse transcriptase. So then RNA viruses, you see the single-stranded RNA with the negative sense, single-strand RNA viruses with the positive sense. What does it mean? It means that positive sense RNA could be used directly as the matrix messaging RNA for translation of the proteins. Single-stranded RNA in retrovirida, in retroviruses, with the activity of the reverse transcriptase, and double-stranded RNA. As you may see, the coronaviruses belongs to the family of single-stranded RNA with the positive sense. What are the routes of viral entry? You see multiple routes of them. First of all, and that's the most important route, the most common route of entry for the viruses, that's so-called clathrin-dependent endosomal mechanism. Clathrin, that's the protein molecule that stabilizes the endosome and permit the endosomal transport and finally formation of the phagolysosome. So some viruses can avoid that, and the aim of viruses is to escape from the endosome in the appropriate time. So exactly the same mechanism SARS-CoV-2 used for its entry to the cell. What are the pathways of viral replication? There are many of them. It depends on the viral machinery. Like big coronaviruses, best example, poliovirus. Just simply attaching to the surface of the host cell, literally inject its RNA and start, since this RNA is basically positive of positive sense, directly start to translate and synthesize the proteins. Finally, we see the assembling of the viral particles and leaving the cell. Rhabdoviruses, the best example, the rabies virus. So you see the interaction. First of all, that's enveloped virus because it contained the so-called supercapsid. That's the biolipid layer around the protein capsid core of proteins of the virus. So it could be entered to the cell again by the endosomal mechanism. But when you see the dissection of the viral RNA to several fragments, and you see the separate synthesis of the viral proteins. Finally, it's assembling partially in endoplasmatic reticulum, partially in complex Golgi, and then leaving the cell, finally assembling directly on the surface. Retroviruses, as HIV virus, you see the interaction with of GP120, that's the superficial protein on the HIV, interacts with target cell like CD4, T cell, T lymphocyte, is CD4 receptor on its surface. Then you see the fusion of the virus directly with the surface of this cell. You see the fermentation of the destroying of the capsid, and finally release of the RNA. On the RNA, using the reverse transcriptase RT, there is occurring the synthesis of DNA. That's so-called provirus. Provirus is incorporated into the nucleus and in the genome of the host, and finally from that point starting to produce its message RNAs and synthesizing of the proteins. Then you see the assembling of the viruses. Adenoviruses, that's DNA viruses. They incorporate directly to DNA. And our today's hero, that's coronavirus. What are the differences? The difference is that this virus, first of all, it's entering using the, as I told you, endosomal clustering mechanism. Then the positive sense or single-stranded RNA on its background, there is the synthesis of negative sense antigenome, and then from that point we see the cleavage of RNA, and these anti-sense, negative sense genes synthesize the positive sense genes. On that basement, you see the synthesis of the viral proteins, assembling of viruses, which occur in both in endoplasmatic reticulum and in complex Golgi, and then releasing from the cell. You see, that's the different routes of the release, and the coronavirus using exactly the endoplasmatic reticulum and complex Golgi to escape from the host cell. And you see the assembling of the viral particles on the electron micrograph directly in endoplasmatic reticulum, and releasing the cell, the assembled particles are releasing the host cell, and for a while they are just in a big company settling here, not leaving the charged cell. So you see the micrograph of the coronavirus, and here you see the schematic of this virus. You may notice the spike protein. That's the very important, critically important protein to interact with the host receptors. And you see the envelope as a double-layered biolipid layer. And you see the nucleocapsid of from the virus. So, a major determinant of tissue tropism is the presence of viral receptors on host cells, as you may see. Like for SARS, that's spike proteins, and receptors for it, ACE2 is the core receptors on the different cells. So, the same for the HIV. As I told you, GP120 binds to CD4 on T cells using the core receptor CXCR4 and CCR5 on macrophages. Physical barriers also can contribute for tissue tropism. Like enteroviruses replicate in the intestine and pod because they can resist inactivation by acids, bile, and digestive enzymes. And as you may know, the SARS viruses, both SARS-CoV-2 and SARS-CoV, also can enter to the body by a gastrointestinal tract, and somehow they can resist the acids. Rhinoviruses, for example, they infect host cells only within the upper respiratory tract. Yeah, but again, to over here, you see the tropism of SARS-CoV-2. This is omnious. You may see different organs, different tissues that finally can be with the attachment of this virus, and through these tissues, this virus can enter the body. That's nasal epithelium, lung epithelium, that's the gastrointestinal epithelium, that's endothelium, that's fibroblasts, etc. So once viruses are inside host cells, they can damage or kill the cells by a number of mechanisms. So there are three major groups of that. That's the direct cytopathic effect, that's the antiviral immune response, and that's the transformation of the infected cells. What about the direct cytopathic effect? Some viruses kill cells by preventing synthesis of critical host macromolecules like host DNA, RNA, or proteins. Also, they may produce degradative enzymes and toxic proteins. Like poliovirus inactivates cap binding protein, which is essential for translation of host cell RNA, messaging RNA. So, like this. Finally, some viruses encode proteins that are pro-apoptotic, like HIV, VPR protein. That's a good example. Next, antiviral immune response. As you may know, host lymphocytes can recognize and destroy virus-infected cells. And who is responsible for that? T killers, yes, that's cytotoxic T lymphocytes. They also can be responsible for tissue injury, as I mentioned before about the HBV. And the last mechanism, the transformation of the infected cells. In fact, there is the large group of so-called transforming viral infections. The good example, that's EBV, Epstein-Barr virus, which by itself may trigger the oncogenesis. It may trigger the carcinogenesis, development of different cancers like Burkitt lymphoma, like nasal carcinoma, etc. As we're talking about the cytopathic effects, that's a very good point to describe its morphological features. You may see that multiple cytopathic effects in this schematic. So there are major 5 groups of these effects. First, that's the cytoskeleton derangement. In that case, eventually we may see the cellular deformation, because no skeleton, no correct shape like this. The ultimate form of this deformation is the formation of the multinuclear cells, the fusion between the host cells which are infected by some viruses, like measles and other paramyxoviruses, but also COVID virus, also responsible for such mechanism. Herpes virus is also responsible for such mechanism. What you may see, the fusion exactly in the tight junctions or desmosomes, formation of the breaches, first of all, between the cells, and after the creation of syncytium, so-called syncytium. That's not the giant cell like in the classic, from the classic point of view, for example, in case of tuberculosis. There is no relation with Pirogov-Langhans cells. That's infected cells. That's like, if you remember the movie Alien, that's like alien. So alien cell, that's not our cell anymore, not anymore. Cellular death via necrotic or apoptotic pathway also could be induced by the impact of the viral activity. Lysis by itself, due to the massive simultaneous release of multiple viral particles, and the most interesting delicious part of our lecture, that's the formation of the inclusions. And now I want to tell you the story about the viral inclusion bodies. So in this table you see the classification of viral inclusion bodies. And the first line, that's intracytoplasmatic viral inclusions, intranuclear, and both types. Yes, indeed, in some infections we may find the inclusions of proteins, of viral proteins within the cytoplasm. For example, Nigri bodies, Garnieri bodies, Paschen bodies, Downey bodies, so-called coilocytosis in case of human papillomavirus, Henderson-Patterson bodies due to molluscum contagiosum, ground glass hepatocytes due to HBV infection. Intranuclear viral inclusions includes so-called acidophilic and basophilic. You see are just four good mnemonics. I provide you with the color. Acidophilic, as you remember, eosinophilic, pink, basophilic, blue, hematoxylin. So for these groups belongs Cowdrey type 1 bodies. You may find them in case of varicella zoster infection, herpes simplex infection, yellow fever infection, so-called Torres bodies. And Cowdrey B part inclusion bodies. You see the difference. Cowdrey A type, that's the inclusion body that consists of homogeneous protein corpuscle, so which is surrounded by the thin rim of the remnants of chromatin of this nucleus of the cell, injured cell. In contrast, the Cowdrey type B demonstrates the halo, so-called halo around the inclusion body. That's the like this. See the pale rim between the inclusion body and the remnants of the chromatin. That's the difference. But for the Cowdrey type B, we may see the variation. It could be either acidophilic or basophilic. So for cytomegalovirus like here, we may see the basophilic type of the Cowdrey body. Examples. Rabies infection. You see the Nigri body in the Purkinje cell in the cerebellum. And here you may see the viral particles stained immunohistochemically in peripheral nerve. See, that's mucosa. That's mucosa, I don't know exactly where. For example, maybe that's the stomach. And along the dendrites or axons of the peripheral nerve, you see the staining, positive staining on this virus. Here you may see the immunofluorescence exactly of this Negri bodies within the neurons. Next example, Henderson-Patterson bodies in case of molluscum contagiosum. Where we are now, we are in the skin epidermis, and you see that the upper layers of epidermis are infected with the molluscum contagiosum virus. In fact, molluscum contagiosum virus, that's the close relative to the pox viruses. In fact, that's from the pox viruses infection. For our lucky pox viruses with the most aggressive, most virulent species are no more exist. Next example, that's the Cowdry type A bodies in case of human simplex virus infection. That's cold sore. So that's the vesicle, perhaps near the lips or somewhere else. That's exactly the bottom of this cold sore, this vesicle, and on the bottom you may see the remnants of the epithelial cells, and in the nucleus, in the nuclei of these cells, you may find the ground glass appearance. That's the accumulation of eosinophilic Cowdry type A bodies. Polycytosis due to infections of HPV, human papillomavirus. You see the hydropic changes, sort of hollow swelling of the cells. These big vacuoles surrounding the deformed and hyperchromic nuclei. The clinical diagnosis: vulvar condyloma acuminata. Ballooning in ground glass hepatocytes. Ground glass hepatocytes. Here you may see the interstitial inflammation, which comprise the lymphocytes mostly, and scattered lymphocytic infiltration you may find exactly in the parenchyma of the liver, and the ballooning of the hepatocytes. Again, this ground glass hepatocytes, that's the result of accumulation of the HBs antigen. See, we may prove that immunohistochemically as the accumulation of viral particles within the cytoplasm. That's actually the same patient. You see there's the biopsy, that's the core biopsy of the liver, and that's the same specimen. Cytomegalovirus demonstrate us the development of Cowdry type B inclusion bodies. As I promised you, with the halo around the inclusion and the thin rim of the chromatin. That's the intranuclear inclusion body. In fact, that's the gastritis in the immunocompromised patient. And we may confirm the presence of CMV infection using the immunohistochemical staining. You see the infected cells, they are brown. Measles. Paramix viruses like measles and paragrippe, parainfluenza infections may demonstrate the formation of syncytium. That's the development of wartine Finkeldy multinucleated cells. On a high magnification, you may find the presence both of Cowdry-like type A inclusions in the nuclei, and you see the eosinophilic inclusion bodies within the cytoplasm. So you see the both patterns, cytoplasmic and nuclear inclusion bodies. What about the COVID-19? It's not the exclusion, because in case of COVID-19 with SARS-CoV-2 virus, the same story. You see the formation of the multinucleated cells, and sometimes you even may find the inclusion bodies, the eosinophilic particles, but in the cytoplasm. Remember, this is not DNA virus. That's why there is no chance to find any changes in the nucleus. And you may see the confirmation of that, the immunohistochemical staining of S protein on the infected cells. So, generally speaking, using the pathogenetic principle, we may classify the viral infections in several types. Uh, first, first type of viral infections concerned with the so-called acute and transient infections. That viruses that cause transient infections are structurally heterogeneous, but all of them can elicit effective immune responses that eliminate the pathogens, limiting the duration of the infections. However, specific viruses exhibit widely different degrees of genetic diversity, a variable that has an important impact on the susceptibility of the host to reinfection by viruses of the same type. We don't know yet about the COVID-19, if it really will be it will be possible way of reinfection if our immunity will be stable against this virus. But the influenza virus can repeatedly infect the same individual because new genetic variants arise periodically in nature. And as we may know, the COVID-19 also demonstrates, unfortunately for us, I mean, not COVID-19, I mean the coronaviruses at all, by their nature demonstrate the very strong, very prominent genetic instability. Next group, that's the viral hemorrhagic fever. Viral hemorrhagic fevers, that's severe life-threatening multi-system syndromes in which there is the vascular dysregulation and damage leading to shock. All these viruses pass through an animal or insect host during their life cycles, and therefore their ranges are restricted to areas in which the hosts reside. So humanocidal hosts who are infected when they come into the contact with infected hosts, like rodents, insects, or bats. Again, bats. Yes, because I'm talking about the fever, hemorrhagic fever, Ebola. So, in case of the hemorrhagic fever of Ebola, you see the damage to apparently all of the cells of our body. Yes, indeed, this virus has the superficial receptors that can interact with apparently all the cells in our body. Why? Because of unspecific site of the attachment. Salicylic acids, that's the universal compounds of our cells and cell membranes, and also lectins, like in case of the influenza virus. So anyway, major targets for Ebola virus, that's the kidney and liver. In this kidney sample, you may see the multiple hemorrhages. You also may see the cytotoxic effect, cytopathic effect of this virus and apoptotic bodies, multiple apoptotic bodies. In the liver, you see the accumulation of eosinophilic inclusions. Oh, sorry, not that. This, and this. These eosinophilic inclusions, the inclusion bodies you may see here also on the electron microscopy. And this is the result of accumulation of viral protein. And here you may see the assembling of the viruses and release from the host cell. And immunohistochemically, we may confirm the presence of this virus within the host cells. And three other groups of the viral infections. That's the latent infections. Latent infections made in vast majority of the cases, there's the herpes virus infections. Latency of them is defined as the persistence of viral genomes in cells that do not produce infectious virus. Dissemination of the infection and tissue injury stem from reactivation of the latent virus. The viruses that most frequently establish latent infections in humans are, as I told you, herpes viruses. So, chronic infections, no, transforming infections. I already told you that's the viruses that can stimulate cell growth and survival by a variety of mechanisms. Best examples that Epstein-Barr virus, that's human papillomavirus, and human T lymphocytotropic virus 1 that may cause lymphoma. Chronic infections with continuous viral replication. The best example, HIV and HBV. What is the peculiarities? In this case, immune system is unable to eliminate the virus, and then continued viral replication leads to persistent viremia. Now I want to finalize our lecture with the understanding of major tissue responses to infectious agents. You must realize that there are 5 major mechanisms of these tissue responses, and honestly speaking 6, because no reaction, that's also kind of reaction. So the first pattern, that's the purulent inflammation. Well-known, old good purulent inflammation that you must know. That's the accumulation of the PNLs, polymorphonuclear leukocytes. Basically, this is the result of interaction with different bacteria, pyogenous bacteria. The best example is the Staphylococcus aureus. Yesterday, if you remember the lecture, if you're present on the lecture of sepsis, you may see, you have seen the same image. That's the brain abscess, is the accumulation of the neutrophils. So what this pattern means? So that means that there is a certain reaction on the chemoattracant, and the chemotaxis of neutrophils play a major role in the development of this type of inflammation. As you may know, lipopolysaccharides of the bacterial capsule may lead to this attraction. Second, mononuclear and granulomatous inflammation. Diffuse, predominantly mononuclear interstitial infiltrates, they're a common feature of all common inflammatory processes, but when they develop acutely, they often are a response to viruses. As you may see here, that's the poliomyelitis, injury of the spinal cord, and development of the perivascular and perineuronal microgliosis. Microgliosis, that's the appearance of the mononuclear cells in the central nervous system. Microglia, that's basically associated with the leukocytes. And granuloma formation, formation of clusters of monocytes which are activated in such a way we call them epithelioid cells. Sometimes they can increase their size due to fusion and formation of the giant cells, and in some cases we may find the caseous necrosis within that. So the aim of this reaction of the host cell is to perform the fence, the barrier around the bacteria, isolate them, contain them from the continuous injury of other tissues. As you may see, that's not really successful. This granuloma formation is occurring in the liver tissue around that. That's in fact hematogenously disseminated biliary tuberculosis. The next pattern, cytopathic cytoproliferative reactions. That's very opposite sides of the moon. You see on one side of that, on one hand we see the lysis of the cells and the necrotic pattern, cytopathic reaction. That's formation of vesicles in case of human simplex virus infection. You already seen the high magnification fragment of this image. That's the skin with the blisters, in fact, and with the necrosis of epidermis, and with the mononuclear reaction against that, because you know basically these patterns are overlapping with each other. But on another side, on the opposite side of this group, there is the cytoproliferative reaction. Cytoproliferative reaction means the proliferation of the cell instead of the necrosis. That's the result of human papillomavirus infection with the formation of condyloma acuminata, again on the vulva. Next pattern, that's tissue necrosis. Tissue necrosis, that's not lysis, like in case of the cytopathic reaction here. That's the lysis of the cell. What is the difference? Because lysis was caused by the release of the viral particles. Necrosis, that's due to the internal mechanisms of the intracellular mechanisms. So how to trigger the necrosis or apoptosis of the cell? Again, that's due to different mechanisms. In this case, we see the yellow fever hepatitis, necrosis and apoptosis of hepatitis, and formation of numerous Count-Silman bodies. Remember, Count-Silman bodies, that's not only belongs to the yellow fever. Also find Count-Silman bodies in case of other different infections, viral infections of the liver. Chronic inflammation and scarring. Some agents may provoke the significant fibrosis with the minimal involvement of inflammation around the infective agent. For example, here we may see the reaction of the hepatic tissue against the larva of Nematodes toxocara canis. That's the forms. In fact, it's zoonotic infection, but occasionally it may appear in human body. It may cause such kind of reaction. See, mainly that's the fibrosis around the parasite, and no reaction. No reaction may occur. Then we see the severe immunodeficiency syndrome, HIV/AIDS. So that's pretty obvious. And we see the development of the Mycobacterium avium intracellular complex within the macrophages. They can transfer this infection from one side of the body to another without any response. So this Mycobacterium, they feel pretty good without any issues. They are just proliferating, disseminating, but normally that's not a harmful microorganism, as you may realize. In this case, we deal with the opportunistic infection. So this infection just used the opportunity of zero immunity, zero defense against this problem. So I want to resume our lecture with such kind of take-home message as a table. You see, in this table there are 6 important steps of the infectious process. What microorganisms need to develop the infection, to develop the infectious disease in some cases. That's the attachment and entry into the body. That's the local or general spread to the body, multiplication of the microbes, then tricky mechanism including evasion of host defenses, then shedding from body, exit, because there is no sense otherwise to provoke the infectious process. That's the ultimate goal for the parasites, to shed, to spread, to contact and infect another host. And sometimes as the side effect, we can see the cause damage in the host. But for parasite, that's just the side effect. For us, that's the most important part. That's what we actually have to deal with. And that's actually the signs, the symptoms of infectious diseases. So thank you for your patience and thank you for your attention. Have a nice evening and thank you for your attendance, virtual attendance of the lecture.